Good. Okay, so let's start this session. So what was the general theme of the class again? We talk about some important coverage problem like set coverage, K coverage, and unique coverage. These are very basic problems. Then we went to the ideal case. So then we talk about general networks. And these general networks are generally graphs. One ideal case for graphs, as we discussed, is to yes. So one ideal case for any graph is to, make it essentially into a tree, because for a tree, we can actually solve the problem easily by dynamic programming. So this was this general idea that we want to try to embed it into tree. And then we had these cut problems. We had the connectivity problem that we want to connect a set of pairs. We will talk more about them. Or sometimes we have the cut problem that we want to disconnect essentially some pairs. And this is like due to security or other things. There are some assignment problems like matching. These are some other type of network design problems, but these are somehow general ideas. And then we try to just match them, or like so try to map them onto trees, and then we lose some Lagrange approximation. So we are continuing that. We talk about some like the problem for cut problems and connectivity problems, and especially for both of them that we had a tree, and then this was this concept of a spanning tree versus just some tree, and then we talked that a spanning tree is much better, but the bonds for a spanning trees currently are not the best. So the lower bound is log n. If we just probabilistic into embedding into trees, this tree is again a Steiner point versus non-Steiner point, but that was not a big deal because you could pay a factor of 8 by Anupam Gupta, the paper of Anupam Gupta, and then essentially remove that factor, like the Steiner points. But the fact that these are subtrees or not subtrees is still something that there is the best bound for just not necessarily subtrees is log n, which is tight, but for spanning trees is log n times log n or something like this, and that is still not tight. That's a very important often problem to make it clean and get a state of the art, and everything will be essentially on the trees. So here I want to talk a little bit about generalization of connectivity and buyatbulk network design. So that is a very important set of problems on the, especially connectivity problem, and there are some nice approaches. And there also another interesting thing is that having a spanning tree versus not a spanning tree can be quite different. In particular, for non-uniform buyatbulk network design, we obtain actually the first polylogarithmic result, and that was one very big step here is to using the results from spanning trees versus regular things, because it was interestingly that was the case that we could massage the optimum using the spanning tree result, but we couldn't use it using like a regular tree result. So that sometime actually can be very important. In general, subtrees are the best. The bound is slightly worse, and again, the very big open problem, can we make it clean? I think the latest one is like Fox 2008, that it has log n, log n or something like this, and removing that would be very important. Good. Now, having said that, let's go through this one. So we want to talk about this buyatbulk network design. This price collecting network design also we will talk about it. And then by dimensionality theory, that's the one that we are talking more about, some kind of a special graphs like planar graphs or bounded genus graphs. These are some special class of graphs. For them, actually, we have a much better solutions and the approach that we can do there. And again, the main idea there is somehow turn into trees, but the trees there, it would be bounded Trivitz graph, which are a generalization of trees. But there we could get a p-task, not Lagrange approximation. So that's like for a little bit more special graphs like planar graphs or H-minor free graphs, this, we can embed them in some sense into bounded trees, which are generalization of tree-width graph. But then we can get the problem is still NP hard. We cannot get the exact algorithm, but they can get p-task, which is 1 plus epsilon approximation, which is much better than like log n approximation that we get here. So that's the general idea that we will talk about them. Again, embedding into tree is like somehow the best idea that we have it for general networks or general graphs. Good. So let me just mention that I want to go these hierarchies. I want to go a little bit from this, and then I will come back to this. So in the Steiner theory, again, I want to go quickly, but I want to now view it as a buyatbulk network design. So this is defined by Gauss in 1836. That's actually a good history to know that. So you are given a graph and a subset of the nodes, and you want to find a subgraph that connects these nodes. So these are like client and the server, and you want to essentially connect them, and you want to minimize the total connection cost. So the total connection cost in this case would be the cable installation cost. For example, you want to connect from here, maybe this guy's to here, directly to here, but maybe these guys you can just connect it to here and then connect it. And you want to minimize the total installation cost or the like total cost. And this is a very practical problem. Actually, I have used this one. I have done some wiring at the house, and I have used this algorithm to buy the minimum number of packages of the wire from Home Depot, because that if you can minimize the total amount of this, then you can save essentially money in terms of the cable that connects essentially the lights together or something like this. Good. So that's a Steiner tree. This problem is NP hard, and of course, it is different from minimum spanning tree. In the minimum spanning tree, you want to connect everything. Now, one simple two approximation for this problem would be this. So you consider, so this is the general graph. We will consider these are the terminals. And these are some of them which are, these are Steiner points. And you want to essentially connect these trees. Maybe you want to use these Steiner points as well. So to get a two approximation for this problem, for a Steiner tree, you can just, consider these terminals. It might be not the whole set of vertices in the graph, but a spanning tree that contains everything. Then what would be the idea is that you want to just, for each of these, you create a new graph. And in this new graph, you just say what is the minimum distance between these two terminals. It may use as the Steiner points, but you will just do it for all of them. Minimum the distance again. But the distance here, it might be 2 plus 2 plus 2 between A and B. And here, if you have A and B, you will put it 6. And of course, if you want to use A and C here, for example, this is another 3, this is C, then it would be 2 plus 2 plus 2 would be 7. So this 6 path and this 7 path, actually they have some intersection. But we don't care. So you just put these ones. Then you are finding in this new graph that has only terminals, you will find the minimum spanning tree or MST. This gives you a two approximation for this network design problem. And this is a network design because here, they mentioned, we are talking explicitly about buying a set of edges or cable installation. So this is a talk that we will have today and next session about buyatbulk network design. And so then at bulk, I will talk more about it, but currently it's just the buy things. So you want to buy a set of these guys such that you minimize the total cost. And here, for example, a Steiner tree, if you want to get log n approximation for that, then you can just use Bartal or FRT or spanning subtrees. You will just embed it into trees. Then in the tree, it is clear which path you need to buy because it's a unique path between these terminals. And so essentially, if you want to solve it, then you can embed this one. Other ways to embed it into some tree, this graph. And in this graph, there is a unique path between all these terminals. So it might be the case. So only those guys that are useful, you will keep them, and the rest you will just remove them. And that you will take the best among these trees, then that would be log n approximation. However, you can get better than that. It's a two approximation. And what is the idea? So the idea is that yes, so here, if you are doing this one, you can consider the from the optimal, if you consider the optimum solution here in this graph, we always do that. So in this optimal things, you can get a solution of size 2 times opt here. And so yeah, like essentially, if you consider the optimum solution here, you can always you essentially by shortcutting you are paying a factor 2. This is the same thing that when you make essentially a graph Eulerian. And then you can pay a factor 2 in this graph, and then MSD is less than optimum, is less than 2 opt. And of course, so here from optimum, we will consider again optimum. We will change it into, we will bring it, massage it into this graph, and we will make a solution of at most 2 opt. So when there is a solution of 2 opt here, then I will find the MST here. So and the 2 opt here is connecting these guys essentially, the no Steiner points. Now, you will find the optimum, the best solution here. That is, of course, the MSD is less than 2 opt. But the good thing is that now the MSD, it has a direct solution here in this graph. Why? Because I mean, these are the lengths of the path. So you can buy these guys and maybe you will pay some extra. But anyhow, we have considered this fact when we consider 2 opt here. So you can always consider the optimum. And I mean, the way that you can do it, the optimum is also easy. So the optimum, say this is the optimum tree, for example, that you have it. So you can start this one. So these are the terminals. And maybe these are the circle ones are Steiner points. How can we make it a tree? So note that in this graph, so this is G prime. In this graph, G prime, G prime, so you have this terminal A and B. So the way is to make essentially go from, so this is the optimum tree. So you will consider this one, you will connect this guy to this one, you will pay the whole path. So this is the shortest path that you are creating it. And then from here to here, you don't want to use the Steiner points here. You will essentially shortcut here. Now this edge has been used twice. But that's the maximum that can happen. Now from here, you will go again this path. So you will consider the optimum solution. In the optimum, the issue is that there are Steiner points. But then you will find the shortest path among, you will find some path among these terminals that each edge in the optimum will be used at most twice. So here you see that this edge has been used twice. This edge has been used twice. This edge has been used twice. Good. Now, these are just paths. But if you replace it with the shortest path, then you will save. And when you change from this tree to these things, you only pay a factor 2 essentially. So that's essentially so that was the whole proof that optimum solution here can be turned into a solution here. And you can essentially, the factor that optimum pays would be 2 times. Like the new solution here would be at most twice the cost of this. Here we are finding MST, and MST is less than 2 opt because MST is the optimum solution for this one. And then MST has exactly the corresponding solution in the origin. So this gives essentially a simple 2 approximation for the problem. However, so this is for a Steiner tree. problem. So that's essentially the whole idea. And this is always we are doing that. So in approximation algorithm, we are considering the optimum solution. Optimum solution generally is NP hard, as we mentioned. So we cannot get the exact optimum solution. We need to massage it. So here, for example, we massage optimum from this arbitrary tree into something that it removes essentially Steiner points. And when it removes the Steiner points, then it would be direct path between them. Then we can get the shortest path. So we get something like 2 times optimum. Always we are massaging optimum. We get some approximation of optimum. But the good thing is that now this new solution that we will get would be a spanning tree on this graph, G prime. Then we are finding minimum spanning tree that we can find it and we can compare it and then we will map it. So we have some bound on the solution of the optimum. Anyhow, this is for Steiner tree problem, one of the most basic problem in the buyatbulk network design. This is a simple 2 approximation. However, this is, I mean, of course, this was some of the slides. We say that always talk about approximation factor, the ratio between the approximate cost and the cost of an optimal solution. Here, for this case, we are always massaging up to get some bound on the opt. Opt should have some structure such that we can compare it. So in some sense, from unknown MP, unknown opt, we are just changing it to something that we can have some grip on that, and then we can compare this. The best, as I mentioned, this simple algorithm, just taking essentially metric completion on terminal nodes and finding a spanning tree, minimum spanning tree there, it gives 2 approximation, while the best one is 1.38. And this is like the one that got, I think, the best paper award in like 2010. So that's for Steiner tree. Now, let's go to the next one, Steinerforest. So here, more generally, we want to connect a set of pairs, like multiple servers for multiple VPNs. So you may have essentially, here, you may want to connect these guys together, and maybe you want to connect these guys together. Good. So you have multi-VPN here. So this is one VPN essentially. This is another VPN. And again, the same problem. So here in the Steiner tree, you want to connect everything to the same guy. Here you want to connect different pairs to each other. And in general, you can always say that so here maybe you want to connect all 3 of them together, but you can say that, okay, connect this guy to here and this guy to here. So this is essentially, you can just say in terms of the pairs always. Or you can connect, say, all 3 of them together. There is no difference. So in the Steiner forest, essentially, you may have a set of nodes that you want to connect all of them together, but you can always somehow describe this requirement in terms of just the pairs. So again, in the Steiner forest, we are given a set of pairs, and you want to connect them. And note that in both Steiner tree and for example, if you consider the Steiner tree here, so what was the idea? If this is the graph, so this is like, for example, 2, 2, 2. If you want to connect all of these guys together, so I mean, if you want to get a direct path, you can pay like 2 plus 2 would be 4. But the idea is this kind of cost sharing. These 2 guys, they may come here, say this is the cost of this is essentially 1. It might be the case that these 2 guys can come to this node, this Steiner node, and then from here they can share their path. And then in that case, we are paying 3 essentially. This is actually, this is a wheel of size 3. You can actually make it a wheel of size n. And if you make a wheel of size n, then this essentially gives the worst case for 2 approximation for Steiner tree using metric completions. Now, so here the whole idea is that in all of this, I'm trying to give the motivation for buyatbulk network design. That when you share, when you want to build some of this, if you share, you get some benefit out of it. And this is exactly the one that we are talking about. How do we want to find the shared things such that you can get the maximum benefit? And so in the Steiner forest versus Steiner tree, everyone should be connected, but the Steiner forest, no. And and again, this is, you can think about this way. So these two pairs should connect. So this is A and A prime, and this is B and B prime. I think there's a long path here. If it was a Steiner tree, you need to connect the whole things together, essentially, all of them together. But if it is a Steiner forest, A should be connected to A prime and B should be connected to B prime. So here you see that actually you can save and this path can be, this L can be very large, like even infinity or very large. So in this case, you don't need to pay this L because these guys can be connected locally, these guys can be connected. I mentioned a very simple approximation algorithm for a Steiner tree. Just take the metric completion, find the spanning tree. It's a two approximation. And then you could improve it to 1.38. For a Steiner forest, unfortunately, there is nothing, but there is it is called moat growing approach. So this is called moat growing approach. And this moat growing, this is there is a one essentially by Agrawal, Klein, Ravi, 1991, and then Gomez Williamson, 95. This is the journal version. I think that was actually 92 or 93, I believe, the conference version. So this is the one that they solve essentially for a Steiner forest and give it two approximation for that. The problem that AKR solved is they have more connectivity, more than two, but Gomez Williamson mentioned actually so they refer to them. They said that the main problem that they wanted to solve was the Steiner forest. So Steiner forest, you want to just connect this one, get a constant factor approximation. This AKR and Gomez Williamson is this moat growing is like a better description of AKR, but lots of people actually citing Gomez Williamson because of a very clean approach. Primaldual. And this, there is a two approximation for that. Now, some interesting things. This AKR this year, it got the test of time award in 30-year test of time award in stock this year. So this is a very important result. And another interesting thing, that's the only algorithm that essentially we know, which is a, very reasonable algorithm. The analysis is not trivial. We will talk later on that one. The analysis is not trivial, but it's not super hard. And you can get a two approximation for this problem. We don't know any other constant factor approximation or like any good constant factor approximation. Indeed, there have been some papers in Fox or other conferences to just say that can we get yet another natural algorithm for a Steiner forest, which is, gives two approximation. And so then they get it instead of two approximation, they get a 96 approximation. And that was a Fox paper. But this all says about the importance of this problem, a Steiner forest. Why? Because the issue is that what is essentially the main open problem? Can we get 2 minus epsilon for some constant epsilon approximation for a Steiner forest? That's the big open problem. So this is the thing that they get it. I think there was this I will actually quoted Guy Kortzer. He was said that these people they improved the approximation factor to the worst. It was the thing. So why you are improving some approximation to the worst? The idea is the importance of this problem. The problem is important in a sense that, as I mentioned, the big open problem, a Steiner tree, you can get it. This was Zilekovsky was the first person who could break 2 and get something below 2, I think 1.9 around this approximation for a Steiner tree. And then it's a lot of set of work, a sequence of work that get 1.38. 1.38 is the best, it got the best paper award this time. For a Steiner forest, there is none. Only this algorithm of Gomez-Williamson or like AKR gives 2 approximation. And it was non-trivial even at that time. Again, the analysis is not trivial, especially AKR is relatively complicated. Gomez-Williamson make it much nicer and cleaner. and we have a good understanding for that. But there is nothing better than two forces. So the idea that the people consider, why they are considering like 96, I think there was another one like 100 or 200 approximation, is the main thing is that can we find another like a natural algorithm that maybe we can massage it to get better than two? Because the issue is that we don't, that is this algorithm, and this algorithm, the people tried a lot and they couldn't get better than two. Then maybe there is another algorithm. And some of this algorithm also, it is not mentioned in the paper. We have for some of them that this is worse than two. They mentioned that the current analysis that we have, say, 96 approximation. But it might be actually, I mean, two already would be great if you can get to another natural algorithm too. Better also, I think they don't mention. But for example, we have, for some of this, we know that this 96 approximation, we have some kind of example that we can say is, it can be actually worse than. But that's the whole idea. The main issue that you can have a Fox paper, like 96 approximation for a problem which has a two approximation, is the importance of this problem, because there is nothing there and the people want to get it 2 minus epsilon. And I think the general conjecture is that, I mean, that should be better than 2 minus epsilon approximation. But this lack of another choice, another natural algorithm, is the main problem for Steinerforest. Not that greedy algorithm. That there is no such. This greedy algorithm is bit generalization. It is mode growing. This mode growing for a Steiner tree would be exactly that spanning tree algorithm.
So that would give you two, right?
That would be two. Yeah. So the mode growing. So the mode growing approach, the greedy. I mean, it's a greedy, essentially primaldual algorithm. For it is interesting. So you can prove that it's mode growing. For a Steiner tree, exactly corresponding to that metric completion, and you find a spanning tree, minimum spanning tree. Yeah. But for a Steinerforest, it's a bit different. It's a bit more general. But that's the only thing essentially that we know is two, and we cannot get anything better than two. Good. So this is so far about Steiner tree and Steinerforest, and both of this problem, this is the whole concept. Sometimes we talk about connectivity, but here I want to talk more about buying enough. You want to buy enough like edges such that you will connect this guy. And that's the view that I want to essentially go more about it, because this kind of buyatbulk network designs are very general set of things which are very interesting in network design. So this is the buying bulk generalization or buyatbulk generalization. So here the idea is that we want to buy bandwidth to meet demands between a set of pairs of nodes. Good. So this is the generalization. So for example, you may think about this way, that you want to connect essentially internet, and different people have different requirements, that how much internet I'm using it. The same thing you may think about electricity or water or other networks. So this is but in particular, networks, essentially, internet is a very important one. So here you want to then demand between different nodes. So in a Steinerforest, you want to just connect these guys together. So you only care about connectivity, but of course you need to buy the edges. There was no demand. You are assuming that each of these guys, they can send infinite demands. But in real world, each edge has some capacity limitations. And you can put a higher capacity, but the cost will be higher. So here, this is the generalization of a Steiner tree. You want to meet the demands between a set of pairs of nodes. And here, cost of buying bandwidth satisfies economies of scale. So here again, these are the guys, like you want to get, I don't know, 2 megabit per second for between these two guys, A and A prime. But here you want to have 100 megabit per second for this B and B prime. And you want to create essentially somehow these tunnels such that they can carry this one. And again, you can think about this one. You want to, here we are talking about carrying in the somehow worst case. Worst case means all of them want to use it at the same time. You may think about it, okay, maybe they may want to do it as, okay, we can have, in general, the idea is that if you don't want to use the peak time, you may consider 90%. Say peak time probably would be 90%. So you need to at least have the solution for 90% of the time. But here we are considering worst case that you want to say that if all of these are using at the same time, how much would be the construction cost? This is actually some things like if you want to do it in the cable companies, like if you are working on the internet companies or cable companies, you have a different type of cables, essentially T1, T2, T3. These are some of them, actually, these are the fiber network thing. And for each of them, there is so this, you have some discrete units, U1, U2, U2, UR. These are the capacities that these guys, they can carry. And then with each of them, there is associated cost, C1, C2 to CR. And here we are again assuming that C1 is less than C2 is less than CR. I mean, if it is not the case, if I don't know, if we have U1 less than U2, and then C1 is greater than C2, so of course in that case it means that just get rid of U2. Sorry, so here, yes, C1 is greater than C2. So in that case means that actually get rid of U1, because here this is a better thing. So you can assume always that U1 is less than U2, less than UR, and C1 is less than C2, less than CR. Again, equality, you can also get rid of them, because if you have a higher cost, higher capacity, lower cost, then always use that option. Good. So here we have this. This is the economy of scale that we are talking. What's the meaning of economy of scale? Means that C1 over U1 is greater than C2 over U2 is greater than CR over UR for these guys. This means that if you buy at bulk, you save. So if you have a higher things, generally you can save. So this is also this is generally, it is called economy of scales. Not always correct. For example, it might be the case is a new technology is coming and the cost for this cable is like high because they are using a particular things. But generally, I mean, maybe there are some other benefits, maybe faster or something like this. And you may not have it, but this is generally things that the people essentially have it and it's very useful. Good. So that's about the economy of scale that we talk about it, and this is the buyatbulk. So, and as I mentioned, if you buy in bulk, you save essentially. Almost any place you go to Home Depot or other place, you will use the same thing. So you can generalize this one and say that in general, I have a non-decreasing monotone concave function, or generally a sub-additive function. So what is this function? The function f of e is from r plus to r prime. For an edge e, where f e of b is the minimum cost of a cable installation with bandwidth b for edge e. So what is this one? He said that, okay, I have a function. I mean, we talk about this U1, U2. I can maybe generalize this one essentially, and that's the interesting things become more interesting and theoretical. Actually, more similar to that, like a generalization of buyatbulk, of course, but also the Steinerforest. So this is like now for each edge, I have some cost. And say that if this is the minimum cost of a cable installation with bandwidth B for HE. So bandwidth B essentially means the flow. That's the reason that we are also use F. So we said that if the flow of B is going through this edge, then the cost of that would be F B of E essentially. And these for different ages may be the same, may be different. And that's the thing that we call it the uniform versus non-uniform buyatbulk.
Because you're no longer restricted to discrete limits,
yes, of course, this is the thing. But also it is a generalization of Steinerforest, because in Steinerforest, we said that, okay, I want to connect this guy and then say infinite demand, essentially. Here, we say that for each of these people, I want to connect S1 to T1, and there is a demand 1 for this. And this demand is something that you want to send it. Now, for the, again, this is S2, T2, and this is the demand is demand 2, and so on and so forth. Now, you want to build, essentially, you want to, like here, you want to reserve enough like bandwidth for them, such that if all of this flow are going through, you can satisfy all of them without essentially violating any age things. And you need to pay for the cost, and at the same time, you want to get also for these guys, you want to have a demand 1, for this guy's demand 2, and so on. This is, again, very practical thing, like I was at AT&T working there. That's one of the most important ones, because there you want to put actually cables under ground. It's at that time was like, I think putting just 1 feet was like more than $50, if I remember correctly. But I mean, now probably much more, because it's like very costly things, essentially. And you want to do it, and you want to put the installation such that you can connect the things. At the same time, you can think about if some person is on top of the mountain, and this is one person, you don't want to bring the best or very expensive fibers, essentially. Actually, this is the idea that you are using the price collecting. So in the price collecting problem, this is the case that maybe for that guy, it is on top of the mountain. You don't have that much traffic. You may not want to connect it through your network. You may want to pay the penalty. By penalty here, the cost. Maybe if this is a cable company X, I don't know, Infinity, for example, or Verizon, you don't want to connect this guy. Maybe you will pay to AT&T. They just connect it through, or like you may pay essentially to this Elon Musk, I think Starlink, to connect them through satellite. So that's the concept of penalty that you may pay. And so this kind of price collecting is somehow also another type of buyatbulk problems that you are considering. We will talk more about this price collecting later. But here we have this FE of B for these edges, and you want to connect these guys. So what is this multi-commodity buyatbulk? Given a set of bandwidth demand pairs, install sufficient capacity at minimum total cost. So this multi-commodity, and again, this is the important thing, the uniform versus non-uniform case. So the uniform is that for all edges, we have the same essentially cost. Non-uniform is that for different edges, you may have a different function. This F of E's can be different. So in the multi-commodity buyatbulk, it is, okay, so multi-commodity buyatbulk, and again, is this F of B? We are assuming it is concave, but more generally, you can just think about it subadditive. And subadditive essentially means that F of A plus F of B is greater than or equal to F of A plus B. So this is, in some sense, subadditive. You can define it as like concave. Concave sometimes is used submodular. It's a bit different things because we are talking about sets, but it's somehow submodular and concave are very similar. Subadditive, we have it. Subadditive is the case that essentially if you are adding these two guys versus essentially linear case. That would be, the cost would be linear or additive. So this multi-commodity buyatbulk is equivalent to the cost distance problem. What is this cost distance problem? This is up to a factor 1 plus epsilon. And the general idea is this one, that if you have this edge FB, This is, again, nice reduction between this. So you have an edge here that has f of b. And again, this is e, we are not. No, this is this function. This function, actually, you can approximate it with a set of linear functions. So instead of this edge, you can put several edges. This is, again, a trick that is used a lot for general f. So whenever you have this kind of functions, you see whether you can replace this one or approximate it with up to a factor of 1 plus epsilon with a set of linear functions. Then what do? Then you have, for each edge, you have two costs. You will say that the cost of this edge. So you have, this is also buyatbulk, they call it rent or buy because of these things. And these are essentially, equivalent. Buyatbulk, we have this f of e that you need to buy it. Rent or buy is like this, that you have this, essentially this one, the cost function. So for each of these edges, you have two things. Initial cost C plus L times the flow of B, or the bandwidth of B, essentially. Good. In some sense, these are very simple functions comparing to this. So FB can be any concave functions, as I mentioned, even subadditive. But this one is just linear function. C plus L times B. Good. And the interesting thing, if it is a concave function or even subadditive, you pay factor 2 instead of 1 plus epsilon. That is interesting, like 2, but you can get 2. Then you can approximate this one with this like this linear function. For each of these linear functions, so this is like, for example, I don't know, this is L1, maybe use another line. Line H1. Yes. H1, H2, H3, H4. Just consider this H1, H2, H3. These are the different things that you are putting it, and you approximate this one. You will put H1 here, H2 here, H3 here, and H4 here. And note that each of these HIs are in these forms, because they are starting from some initial cost and doing that. Why does it work? This is a very interesting and general reduction. It can be used for lots of other problems, that, for example, for facility locations or other things. That whenever you have this function, you can actually put it by this, if it's concave, you can approximate it by this set of lines. And then what will happen? In some sense, when you put these parallel edges here, you will take minimum of these linear functions. And this minimum is exactly this concave function that we have. So it's a very general approach, and you can do it, but this comes essentially to these functions. In some sense, we try to generalize this one and say that, okay, this is a set of cables, and we have this one, and say, okay, this is a special case of this concave function. But then this concave function, we try to simplify it and bring it into this version of the problem, that on each edge, we have some cost function, which is called installation cost, plus some per use or renting. This is the renting, essentially, cost. Or like maintenance cost, or I don't know. This is the length function. This is called length function, which is E of, essentially, this is per usage. So it, depending to your usage, you will pay that. And again, if you have a concave function, you can approximate it with this one, and you can approximate it with this function, and then you can put, instead of one edge here, I will put a set of edges here. So this is some kind of reduction, and then I'm using a 1 plus epsilon for concave, and factor, this is 2 for subadditive. So what is the problem? So in some sense, we went there, and then we came to this problem. So what is the problem again? You are given a set of pairs SITI and with a demand traffic DI between them. And the goal is to minimize the total cost of installation plus route. So this is, now you can see that it's actually much, maybe, I mean, this is another view of, again, another generalization of Steinerforest. Because in Steinerforest, you say that we have only installation cost. So in Steinerforest, only installation cost. Only we have this function C, because you will just pay, then there is, you can infinitely use it. But the issue is that in real world, you cannot infinitely use it. So for any additional thing, you need to pay that. And now that's the thing that the demand pairs essentially are. So that means essentially the generalization, it is a very clean one. And we want to work more with this cost distance function, and we call it cost versus distance. That's the things that we are talking about. So this is the formal things essentially in the cost distance. You are given a set E prime of E such that all pairs ST are connected in G of E. So you want to essentially, you want to select a subset E prime of all edges. And for each of these edges, we have this function that we have. So you want to minimize the cost of this. C of E prime is actually the cost of installation cost for all edges in E prime, plus for each, essentially for each demand between these guys, the DI, you need to pay DI times LE prime of ST. What is this one? LE prime is the shortest L path in G of E prime. So that is important now. So what is the thing? So we change it a little bit. I mean, like make it more formal. So you want to, this is the whole graph. This is the demand that are given to you. You want to buy a set of essentially things such as these demands are connected. Now, how much is the cost? Of course, the installation cost you need to pay for each of them. But when you pay the installation cost for each of them, then what about the rent? Then if you have all these edges that you already bought, between any of these guys, then you need to pay per demand, pay per unit of use. You will find the shortest path in this graph in terms of these L things, and you will route them because now you know that DI times that would be the cost that you need to pay.
What do you mean by L path? You mean this is
this is the shortest L path. L path means according to L. According to distance. You see here in the previous one, L was a length function or a distance function. Or each edge had some, I mean, this you had it some cost E to buy it, and then it had some length. This length essentially is the one that it has it, and that times essentially. So this is per usage. Like if you have a larger things, then essentially you will you need to pay per unit more. So now that so in some sense, first you decide which edge you want to buy. It is not completely like this. You need to get a trade-off. But if you know, this is the thing, if you know which edges E prime you want to buy, then the rest of the problem would be easy. If you know which edges you want to buy, then the rest would be easy. Why? Because then you will see what is the shortest path according to L prime. Now this is the set of edges, that's the best that you can do it. And then DI times that is the cost, that extra cost that you will pay. And of course, the whole idea is somehow the trade-off between this part and this part. Because if you buy lots of edges, then you can, have if you essentially buy all set of edges, then you find the best essentially rent cost now, because you will go the best. But of course, then you paid a lot for the buying set of or installation cost. So this is the concept of cost distance essentially that we have. So let's see just one example here. So for example, here, assume that this is the example. These are the pairs, those that have the same color or the same, these are the demand. So for this guy, say, so all the demands here, we are assuming that. So the demands, even you can consider di equal to 1. Even that is interesting by itself. So here, but this is the catch. Now, if so why even demand 1 is equal, interesting. Why is not a Steinerforest? Because whenever these guys are sharing the edge, there is some installation cost that they can share, but the renting they need to pay. So another interesting thing, if all this rent cost is 0, if all this installation cost is 0, then it would be the shortest path. Each person you want to find, just find the shortest path according to L and route it through that.
If EI demands were let's say 0, but let's say very, very small, would that
for that case, yeah. So that you can think about if they are very small, essentially comparing. Yeah, you can essentially multiply the demand. Say the demands are generally much smaller than the installation cost. You can, because you can multiply this installation cost a lot. So you can say the demands are 1, but the installation cost just multiplied by a very big number. Then these demands will essentially be nothing. Just the installation cost would be that. That would be Steinerforest. So if the essentially if demands comparing to this installation costs are very small, and there of course, or another case you can think about it actually, a generalization is L is equal to 0. That's also another generalization. Or if the distance between any pairs, L distance is 0, that's also is a Steinerforest. So you can think about, yeah, demands are very essentially small, that the L cost will be 0. So in some sense, in both cases, the L cost, the rent cost is 0. Either the demand is so small compared to installation cost by some kind of scaling, or we don't have essentially rent cost. Good. So in this case, the contribution. So for example, here you can think about it. So but the catch is this one, that this is different from Steinerforest, because you need to pay per essentially. So if you share an edge, part of the installation cost will be shared, but still you need to pay the rent cost. So if you consider this edge, for example, here for this edge, the installation cost is 14, and the L is equal to 1. Now, 2 demands are using it. So one demand is essentially this one that is connecting these yellow guys, and another one that is connects these red guys. So there are 2 demands that are going through this one, and then there's the installation cost of 14. So this edge, you will pay 14 plus 2 times 1, which is 16. You will sum it up over all edges of the graph. That would be your total cost. The contribution of this edge to the total cost would be, this is the case that this is you only pay for rent. So there are 2 guys that are using it, and then it would be 2 times 3 would be 6. Good. So here there are two important special cases of this problem. One is the single source case. So it is called single source buyatbulk. Here all SIs are equal. So in some sense you can say that a Steiner tree is a single source version of Steinerforest. So Steiner tree is a single source version of that. Why? In the Steiner tree, you can say that I want that everyone is connected to one vertex. And of course, this vertex can be any vertex, but this is somehow the rooted version of that. So here, this is the case. All of them, all the S, and again, we can think about all SIs are the same or all TIs are the same. Doesn't matter. This is called single source. Another thing that we will talk about it is about the uniform case. So in the uniform case, the cost and length function are the same on all edges of the graph. So it means that in each edge E, we have the cost C plus L times the demand passing through it. Good. But here, C and E are independent of edge. So this is C and E are independent of edge E. And this is called uniform. We will talk actually about both of them. And this uniform case was much, I think it was around 90, and I will talk about it. That you could actually, the people know the solution. That is essentially, you can just doing it just using FRT or Bartal or others. But there was a Fox paper even for the uniform case, but you will see that how easy is the current technology. Single source also, the problem was known. So this is essentially the things that was there. So there's a log n approximation for some special cases. So for the single source cases, essentially, so for single source, there are, I mean, these papers, I mean, each of them, like this understanding that I have mentioned about buyatbulk, F of E, etc. This has happened in a series of papers. The people didn't know at the beginning these problems are the same. And this was buyatbulk. There was another problem called rent or buy. But actually, it turns out these problems are the same or almost the same essentially. And these are the different approaches that the people took it. And there is, for this one, for single source, there is a log n approximation. For the uniform multi-commodity, also there are several things. This is the one that we talk about. I will talk about this Averbach-Azar, 97. They had the first essentially algorithm using some variation of Bartal, but that was actually more complicated. But then using the Bartal and others, you could actually improve. And another interesting thing, almost logarithmic hardness for almost this case. This is the Matthew Andrews paper. He said that for this problem, you cannot get better than log n approximation. Note that for Steiner tree and the Steinerforest, for both of them, we could get constant factor approximation. But as soon as you will become buyatbulk, then there is no better than log n approximation. This was the Fox paper. So these are like a very important set of problems. So this problem was essentially open. No algorithm with polylogarithmic approximation factor for the most general case of multi-commodity non-uniform buyatbulk. So here for single source it was, and here we will call it multi-commodity. Whenever we will mention multi-commodity means Steinerforest type of thing. It means that there are SI TI pairs and there is some demand between them. That you will hear multi-commodity a lot in network design means that we have this kind of pairs. And for this one non-uniform buyatbulk, there was nothing essentially known before. There was a paper actually by Moses Charikar. They got it something like 2 to the square root of log n, if I remember correctly. But there was no polylog approximation. And that was very complicated essentially. So until this result that we had it in Fox 2006 and SciComm 2010, that you can get this one. For each number of SITI pairs, we obtain a practical, it's a very nice and clean algorithm with approximation ratio log h to the 4. So, and that is interesting. So if h is small, then this is not log n, it is log h essentially. And I mean, here we will talk about this one, the case that essentially all the unit demand case, and we present O tilde log n, means there's some log n here. Well, but you can improve this one to log 4 to the h. There are some improvement after that, as I mentioned. You cannot get better than log n. I think we had even log n to the 3, maybe log n to the 2 is known. But this one actually was the first algorithm that could break, that was essentially very breakthrough result at that time, that could, for multi-commodity, you could get polylog. And one thing that made it possible was this result of Spillman, Tang, Elkin, another author, who showed that actually you can get, you can embed into spanning trees with log n to the 2 distortion. Later, it has been improved to log n, log n, or something like this again. But this was a very important result. Before their result, they had also 2 to the square root of log n. That was not good, but not better than Moses Charikar's paper. But this one, we could do it. So we will talk more about this one. And in particular, also this, we will start with this uniform case. We talk about single source case. And this general approach for multi-commodity case, this algorithm, you should be able to see the whole algorithm and the technique that has been used. We will talk more about them next time.